Hi, how's it going? We're a little bit late, I think, so I'll try to rush through some stuff. Hello, Armenia. Barev. Yes. Some of you may know me. Who I am is not that important, so I'll skip that. Let's go right into the meat of the talk. We're going to talk about building language, or in particular, building a language here. You may ask, why would I want to build a language, right? And for centuries, humans have invented different sets of tools to deal with different problems. In this particular scenario, language is just a tool that serves to communicate, synchronize ideas across individuals, across our heads. You can understand me because we built a language, English, right, in this case, that all of you understand, right, that you can sort of decode in your own head and build some internal state just as I encode my internal state into the language. It's kind of cool. So language is a tool that solves problems, right? Particularly, programming languages solve more specific problems. We have languages like Lisp, McCarthy's Lisp, which was thought to bring intelligence to computers. Languages like Armstrong's Erlang, which is a great system for building distributed systems. And it's a language that was built to build programs that can run forever. And we can think of languages like Milner's ML, which were essentially thought to build programs that can never crash, right? But let's look at an example. Actually, let's do a few examples. Erlang has this idea of mailboxes. How many of you know what a mailbox is? I see one person. Okay, so this is probably a bad metaphor. A lot of people are aware of it, but what did they mean when they say a mailbox? And because the language was built in Sweden, is the idea of a mailbox tied to the idea of a mailbox in Sweden? I don't know. Someone has to define that, right? Same for JavaScript and promises. We have a rough understanding, very intuitive, of what is a promise. Right? I promise that I'll do something, and then you expect me to come back and say that I will. But some of the languages have different metaphors for this, such as futures or tasks, which is not very different from, hey, could you do this for me? And you say, like, yeah, I will, and then you eventually come back. CSS, in particular, deals with a lot of metaphors as well. They're not as obvious, right? But we talk about classes and selectors and font families and colors and all these things, right? But you have to ask yourself, what are these things? What is a valid color? Someone has to figure it out. Someone has to define what the valid color is. Essentially, the process of building language is the process of finding good metaphors to solve a particular problem and teaching that metaphor to a computer. All right, so let's build our language. Are you on with this? Yeah? Cool. All right, let's do it. Good. Let's begin by how. Does anybody here know how to build language? And I bet some of you use languages. Maybe a few of them have built one. I'd say that there's essentially 3 bits that we need to define 100% to be able to build a language. The first one is that we need to list what we know about a problem. If we don't know what problem we're solving, then there's a good chance we'll build the wrong language for it, right? We need to define the grammar. And this may take you back to school when you're learning the rules of syntax analysis, like, okay, this is the predicate and subject and so on. But the reality is that programming languages are, to some extent, languages, right? So you need to define what is valid. And once you do that, you need to figure out how to evaluate your program. What does it mean when I say something, right? There's some semantical rules that help you understand what I'm saying. So we're going to explore this by building a tiny language that works with colors, right? Does everybody love colors here? All right. I did not think of this through. Is there anyone that's colorblind? The 2 colors that we have on the screen are of different colors. I hope that's okay. Colors live in spaces. Spaces, we're going to say in a second, are just like in math, just n-dimensional arrangements of values. They have components and they can be combined. We can all agree on these things. They're pretty essential to colors. We're going to be working in Rgb Space, and the idea of color spaces comes from maybe 1802, where some people were theorizing that humans perceive colors using different perceptors. Some of them catch reddish wavelengths, right? Some of them catch like greenish ones and blue ones, and then we combine those internally and build this idea of what is a color. So if you see a space, you see that you have these 3 dimensions, and you can figure out that RGB 40, 90, 80 sort of fits in that point, 40 for red, 90 for green, and 80 for blue. So we would normally write it like something like this. You have RGB, and you put the names of the values there, 25500, and you say this is called red, and then light red will be some shade of gray added to the RGB, right? If you add more to a color, then it becomes whiter and whiter and whiter. But really, why is this valid? And what are we saying here? Are we saying that red is RGB 25500? Could we have called that like ABZ? Would that be the same? Is the position of the numbers in there, does that correlate with the name of the function we're calling? Are we calling a function RGB that takes red, green, blue? Could it be the other way around? If we call B RG, will it be blue, red, green? Like, where is that defined? So let's define our grammar, right? We're going to define this, and you'll see that it gets a little tricky because we need to use some language to talk about another language, right? So bear with me. We're going to first define what is a color. And we're going to say a color, right, can be composed by using this sort of symbols together. If you put the words RGB, right, and then you put a parenthesis, and then you put a number from 0 to 255, and then a comma, and so on. Is that, Rito, can you follow through with that? All right, cool. Then we get a color. So we can very quickly grab a few examples and say this is not valid. JK, not valid. RGB 1000, that's not valid. The value's out of range, right? RGB 255, 255, 255, that's 255 million something. It's too high as well. And also we have one component, which is one big number. So we need these three components. They are defined somewhere. And to define that very, very precisely, we're going to use a notation called BNF, Bacchus Naur form. This was invented by John Bacchus back in 1959 when he was formalizing the Algol language. The date might be a little off, but around that time, he came up with this language for describing all the languages. There's a lot of tangential work related to what Noam Chomsky in the field of linguistics was doing. Look into that. It's incredibly interesting, but we need to stay in focus. So let's define that. And you'll see that this is fairly similar to what we just did. We just extract the color part so we don't repeat ourselves, right? And we say that color will be some sort of symbol, and it will be defined by this colon equals means defined by in that language. Right? And we have the color below where it says from 0 to 2 is the first digit, from 0 to 9 is the second digit, and from 0 to 9 is the last digit. So far, so good? Is this color valid?
No.
Are you sure? Right. So the first digit is 2, the second digit could be from 0 to 9, and the third one from 0 to 9.
Okay, sir.
This is valid in that grammar. But of course, it's not a valid color that we can represent. So we're going to have to chunk this down a little bit more. To do that, we can introduce a little bit more complexity into that meta language, and we use the pipe to define options. It could be this first line or the second line and so on. So you'll see that either we go from 0 to 1999, or we go to 2 to 249, or we go to 250 to 255. And then we have more or less what we want. You can still write 000, and that will be valid, but it's less meaningful. It's okay. Like left-hand side zeros, we don't care about those. So now we need to figure out how to give names to these things, right? So we need to define what the hell is an identifier. Why sometimes when we write a variable name, it says, oh, doesn't work. Like you put like a bang in the middle. Somewhere in some spec says, the identifiers are valid if they follow this rule. So now we can think of blue, red, and not red as valid. And you'll notice that there's a space because in the last slide, right, we actually have space right before the star. Okay, so we have the colors, they're valid, right? We want to have some operation to add them together, right? Thank you so much. And we'll define an operation for adding colors. And we can add colors either by name, like red plus gray, or we can say RGB something plus RGB something else, right? Now, this error may look very familiar to you. This is something that happens when you don't follow the grammar of the language. If you type something that doesn't make sense for the grammar of the language, you get one of these. And the program that gives you this error is a program that reads some data, whatever you type, uses this grammar to figure out whether it makes sense, right? And lifts that data into another format. And this is called a parser. That's like vox populi, the way that you would call it. And a parser is just a function that takes a string and returns you, when it's good, it returns you an AST. We'll see what that's in a second. Otherwise, it returns you some error. The problem is that if you leave that text into some data, you need to figure also out how to shape that data in a standard format so that everybody that can read that structured data, right, can process it and do different things. We call this AST an abstract syntax tree. It's essentially a bunch of objects, right, or arrays or lists or whatever you're using in your language that lets you represent exactly the same things that you're writing in your code. Let's look at an example. RGB 10, 20, 30, when it's read by this parser, could be turned into an object that says key red 10, key green 20, key blue 30. That was so hard to read, I don't know why. All right, so we have that. We can lift some text now into a structure. Now our program can operate on that. We'll do the same thing for binding. Binding is the idea of giving some value a name. It's also called assignment in some languages, but the idea of binding is that it cannot be replaced. So you can mutate the same thing. So if we do red equals Rgb something, then we get this structure there. And I'm making this up, right? I'm literally just saying, well, I think this will be a good representation for that text. And you can do the same thing. Like all of the languages that you use have had a person like me in that position saying, I think this is a good idea, I'll do it. And then some of the people say, no, that's probably wrong, and then you debate and you find something that works. But if you lift that data into a program, right, how do we know the program is not just going to add RGB and come up with a number and just print it out on screen? Like, what does it mean, right, to have this data? And how can we operate on it? What exactly should we do for our language to be our language and not something else? For that, we need to define the semantics. The semantics is a fancy word for saying what things mean, right? And in particular, we're going to be using one tool, one very, very good tool for working with semantics, defining them, called operational semantics. This is where the talk gets a little dense, but I promise I'll try to be as clear and slow as possible. So if you have any questions, just save it for the end, and we can go back to the slides and go through them, or after the talk. Operational semantics lets you define how a language behaves, right, by thinking of a tiny machine that when you give it a word, it does something. And as you throw more words at it, that something changes, right? If I give you a number, right, you say, well, I have the number 1. And then I give you number 2. Right? And then you say, well, I don't have number 1, number 2. And then I throw you the plus sign, right? And they say, oh, okay, well, for a plus sign to work, I need 2 numbers. I have 2 numbers. I'm going to add them together. But the result of adding has to be another number. And that's something that we agreed upon. So let's look through an example. If n is a name, and e is an environment, and n is not in e, then n is unbound. All right? Does that make sense? A little bit, not too much. Let me rephrase this in a slightly more formal way. Given an environment E and a name N and a value V, N equals V creates a new environment E prime that is the same as E, but with N bound to the value V. Does that make sense? Well, the reality is that writing these things in English is incredibly complex, and it means that everybody has to have the exact same interpretation of that English language. So English is a horrible tool for doing this. Any natural language would be terrible for this, because I don't speak Armenian, so if you're writing in Armenian, then I can't implement a parser for it, or an interpreter. So what we do is that we define another language, right, that will help us define these tools. And this language is very simple. It only has this form. You have some conditions above, right? And then below you have a grammar rule. So if you find that rule, like some name equals some color, then you have some result. So you can read this as if conditions, right? When grammar rule, then result. We also give this rule a name. Very quickly, for the sake of space, normally you abbreviate things. Perhaps unnecessarily, but I'm going to do the same thing, so when you go out there and try to read some of these things online, you don't find that, oh, well, Leandro has all the big names, and now I have to get used to this thing. So I'm not going to lie to you. E will be an environment, N a value, and so on. You don't have to memorize this. It's just the initial of whatever we're talking about. Let's do this. Ready? No. Okay. We have binding of names. This says that if there is an environment, if there is a name, and there is a value, right? When we find in that environment that the name equals the value, so someone writes down in the program red equals this value, right? Then we come up with a new environment where this name, red, equals some value. I think I lost everyone here. It will be clearer in a few minutes when we go through an example and show. I have 15 minutes left. Perfect. Okay. So I have 5 minutes more than it looks here. Awesome. Color creation. If there's 3 colors, X, Y, and Z, we don't care about which one of those colors are, right? And someone writes down RGB, X, Y, Z, right? We get, oh, sorry, I have an error in my slides. X, Y, Z should be numbers there. If someone writes RGB with 3 numbers, right, then we get a color back. The result of calling RGB, it's a color. Color addition says that if there is an environment, right, and we have 2 colors, Z0 and Z1, when you write down red plus gray, the result always has to be another color, right? These are rules so that when you build a program that will run this language, you need to follow. V8, for example, for JavaScript, has rules like this that says, well, the semantics of JavaScript dictate that when you create a promise or when you use the new keyword, right, this happens, and so on and so forth. It's something that people agree on. So now we can look at this and say, all right, we have red equals RGB 25500, gray equals RGB 128, 128, 128, and then we have red plus gray. What should be the result? Should that be another color? Yeah, I thought so too, right? But so far we have defined the addition in terms of colors, not names. So we could say RGB something plus RGB something else. You know, that gives us a color. But if we say red plus gray, what is red? Red is not a color, it's a name, right? It's a variable. It's like, this is not the value of the variable yet. To do this, to be able to interpret this, we need that rule for expanding a name. For saying, if you give me a name like red, and that name turns into a color, right, then whenever you use the name, we'll just use the color. So essentially, if you have a variable and you use it somewhere, the person doesn't get to use the variable. They use the value of the name. Otherwise, const name or const a will be equals to some a that you don't really can manipulate. Can you change the name of a variable? Oh, you define a new one, right? It's like outside of the control of the program. So after this, we can look at that slide, right, and say, all right, red, RGB, gray, right? We add them together. We can expand them, right? And now we can actually add them together. This is sort of the way an interpreter or compiler would work, right? It will essentially go through this code, applying some of these rules, saying, oh, well, this is what I should do, this is what I can do, and so on. We'll see a full example in a second, just I think 3 slides away. There's just one problem with this. Do you know in what order to read this?
No.
You would assume that it's like first and then second and then third, right? But there's some languages where that is not guaranteed. Some languages, right, will let you define everything everywhere, and they do something else. They read it bottom up or randomize the ordering. Languages like Haskell, for example, they don't actually have a guarantee in sequencing. They can run everything as, disordered, and it should be okay, because that's what the language is built for. So we need to define our execution order, right? And in addition to that, how exactly does this plus operation work? We've said that when you add 2 colors, we get another color, but how do we add those colors together, right? So we need to define that as well. Like if you do promise.then, somewhere is defined that then means this thing. All right, so let's do the sequencing part, right? This is so exciting. So here we define that. On the rule above, both rules are called sequence. They have 2 cases, right? If there is an environment, and we have an expression that evaluates to another environment, then if you have an environment and 2 expressions one after the other, right? If you write down red equals something and then green equals something else, that's one expression above, the binding of red to the value. The second expression is green equals to the value, right? Those evaluate to the new environment of the first one, and then the second expression. So then you go back to the same rule. It's kind of like recursively consuming the rules and building up an environment for each one of them, which is what lets us say red equals something, gray equals something else, red plus gray. You need the first one to create whatever red means, right? The second to create whatever gray means, so that the third one can be like, oh, okay, I know what red and gray are. And in the second one, right, we're saying that if an expression evaluates to another expression, right, and changes the environment, then if you give me 2 expressions where the first one changes to another expression first, then we go through that first. Let me go through that for a second. Let's say you have green equals blue plus yellow. Blue plus yellow, right, are an expression, and they evaluate to a color. So before we can say green equals to this color, we need to say blue plus yellow. So we need to deal with that. And this one guarantees that you will go through one, and then the other, and then the other, and so on. This gives you the ordering in which you evaluate, you understand, you read your language. Let's do an example before we get too far in or out. We have this example of code, and we'll read this in this way. whatever's in brackets is just a comment. Whatever's on braces, it's something that you as a programmer don't see. That happens when you run the code. We write down RGB 000, right? We press enter, or we make a new line. What happens here is that the interpreter will say, oh, this is the color creation rule. And then it goes back to the little rule that we wrote before, right? And it evaluates it. And it turns out the rule creates a color but doesn't really change the environment. So the environment continues to be empty, as you see on the left, right? There. Now we go to the second one and we say red equals RGB, and then there's a color. First, we create the color with the color creation rule, right? Once we have a color, we can actually call the bind rule to say this color will be associated with this name. And you see that on that line, when we run that line, or while we are running it, the environment is still empty. But immediately afterwards, you see that the environment has something called red. Am I good with time? Good, thanks. Oops. Now, if we go to the third one, when we have an environment that says red, we run again through the same process. We read that code and we say gray equals RGB 128 3 times. We say this is the color creation rule, right? So we apply that, we create a color, and then we apply the bind rule, which means, boom, we created gray as a color now. Next one, we have environment that already knows about red and already knows about gray, so we can use those colors to do something together, like add them. And in this case, we want to use light gray as a new color that we define by combining these two colors we had before. So you say gray plus red. First thing we do is we don't have a rule that deals with names and addition, right? But we have a rule that expands names into colors. So let's apply that rule. We apply that rule, and then we end up with RGB for gray plus RGB for red. Thanks. And we can apply the color addition rule there, right? Each one of these rules will be like a tiny function if you're in your interpreter that just takes some data in and says, okay, this is what I do. If you call me, then this is the only thing I do. But when we go through that rule, we define that we will get a color back every time we add two colors together. But how do we add them? That's the part that we don't know. We don't really know what to bind to the name light gray. All right, let's go back to color theory a second. Additive mixing is a way of adding colors in which each one of the components of the colors, right, increases only. So you overlay colors, right, and the only thing that you get is a color that is brighter, closer to white, whatever white is. If you're working with colors from 0 to 1, like 0 point something something until 1 for each component, then white will be 1, 1, 1. In our case, we're using 255 as a limit from 0 to 255. So adding two colors means that we increase each component, we add them together, right, until they reach white. So we could say that we can write that addition as this. If you have some color, R1, G1, B1, right, color 1 with 3 components, and another color, R2, G2, B2, so second color with 3 components, when you add them together, you get the addition of the reds, R1 plus R2, right? And then the addition of the greens, and then the addition of the blues. But those values are capped, which means if the addition of those is over 255, we just stick with 255. This means that if you have two colors that have, 255 and something, you don't get 512, 511, I guess. Yeah, 510. Yeah, you get 255, right? It's like saying that's the limit. You can add how much you want there. It's never going to go brighter than white. So now that we know that, we define that somewhere, right, as a spec outside of our code. This is just a little bit of math, but it also looks like a small Haskell program. Now you can go through the example that we had before and say, all right, when I apply the color addition rule, what I get back is this color, 255 and then 128, 128. Because 128 and 0 will end as 128, and 128 plus 255 will be bigger than 255, so we end up in 255, the cap. Immediately afterwards, we can apply the bind rule, and then we have 3 colors in our environment, red, gray, and light gray. Now, this feels like a little bit of a made-up example, so why would I actually want to go through this? And the idea is not for all of you to run home and just start building your own programming languages. If you want to do that, please reach out to me. It's an incredibly fun exercise. But rather that you would go back home and see the code that you're writing and ask yourselves, why does this work this way? Who thought this was a good idea? And where is it written down that it has to be this way, right? Now, this is not to bash on anybody, right? Sometimes we have to make decisions. Someone may think, oh, maybe additive mixing for colors is stupid. Opinions, we all have them, right? But it's useful. It's very useful for some things. I think it's incredibly useful. All right, next steps. There's not much more to building a language, right? But that's also a terrible lie, than defining what the language would be. What can I write? What does it mean? You have to build your interpreters. You have to build your parsers. This is not a talk about how you can type in your language into your own compiler. This is a talk about how you can think about your language before you get there. You may be enticed to just sit down and say, yeah, it's going to have addition and then also promises and this and that. And then you end up with a mess of a language that it's very hard to make sense of. Fortunately, the web has a few people that are actively working on making sure that the languages that we use make some sense, right? With the W3C, the World Wide Web Consortium, and the TC39, these are groups of people that are actively working on making sure that the web evolves in a way that makes sense. You can collaborate with that. It's completely open. You can submit your proposals, right? And the output of these groups are specifications, sometimes reference libraries. For example, ECMAScript came out of a consortium, came out of a group of people that decided this is what the language should look like. JavaScript then started to implement ECMA. There's also RFCs that define different languages, such as JSON. So if you read the RFC for JSON, then you can learn the syntax and you can build your own parser. You don't need Node anymore to say like, oh, I'm going to work with JSON files, for example. But yeah, to save you guys some trouble, I'm gonna give you some tips and tricks. There's 4 books that are incredible, and if you don't like to read, have one of your friends read it out loud for you. Programming Language Foundations, TAPL, and Dragon Book, and I realize now that the authors of the first 2 are wrong, and that should be Pierce, not Aho. Are great books to learn about programming languages in general. Not one specifically, but like, what are languages really? The Dragon Book, and you can search by that, it's not called Dragon Book, but it has a huge dragon in front. People call it the Dragon Book, it's just the way it is. It's an amazing book for learning about how to build compilers. It's a book that will teach you how to take the ideas that you've learned today, right, and start writing programs that can read your own language and run it. And Software Abstractions by Jackson is a very new book built on very interesting ideas about model checking. We're not going to get into that. Maybe next conference, if you guys have me again. I love Romania. It's an incredible country. But it talks about how we can very, very quickly reason through all the possible combinations of things, right? And make sure that there's nothing in there that is broken. And with that said, merci. I guess we have time for like half a question. No worries. You can find me outside, out of the booth, I guess. Yes. Thanks.